One of the last things that we're going to need to be able to do when analyzing projectiles is not look at just projectiles that go completely horizontally off of a cliff or are fired at a degree of zero, technically. Would be situations in which, more realistically, an object is launched at some kind of angle, such as maybe a soccer player kicking a soccer ball, a football player punting the ball, a baseball player hitting the ball. Most projectiles generally are not always fired or launched perfectly straight. There's usually some kind of angle. There's two specific situations which we're going to analyze. The first being the starting and ending elevations are exactly the same. That would be something like kicking a soccer ball from the ground. It goes through a parabolic arc and lands at the same elevation. That's one type of condition. The other one would be different starting and ending elevations. So something is launched from the top of a cliff, goes through its parabolic arc, and either lands above or below where it started. They're only slightly different situations. There's a few concepts that apply to one but not the other, and vice versa. We're going to start in this video just analyzing the same starting and ending elevation. We'll visit different starting and ending elevations in a future video. So for right now, they're not drastically different, but we're going to focus just on the same starting and ending elevation so you can grasp some of the concepts that pertain just to this situation. So if we want to start to look at these problems, we need to just think back to the last thing we looked at, which was analyzing the final velocity of a projectile. So if you remember in the previous video, right before that projectile hit the ground, we spoke about the fact that it had a certain vertical velocity. At the same time, it had a certain horizontal velocity. And when these two were combined, that gave us the actual velocity in the actual direction that the object was traveling in. Analyzing the initial velocity is identical. It's exactly the same, except that usually when these objects are launched, they're still traveling forward. There's some kind of forward initial velocity. A lot of times, if they're fired up at an angle, they'll also be traveling away from the ground at some initial y velocity. So if you take a look at these two diagrams, you should see it's not that different except for the fact that usually the final velocity for a projectile in the vertical direction is down, and in the initial direction it's usually being launched up. But you can see they look fairly similar, so the process is going to be identical. So here's an example. If you were asked to find the initial y and x velocity for the following projectile, we'll take a look at how we would do that. So we have a projectile, some kind of rock or ball, and it's being launched up at a 30-degree angle. And we're given that its initial velocity is 8 meters per second. Now don't confuse yourself, that's not the x or the y component. That's not the forward or the vertical component. That's that combined x and y velocity. The projectile is moving up off the ground while at the same time moving forward. And when those two things happen together, this object can be seen to be traveling at 8 meters per second. So if we come down here, we just have to use our right triangle geometry and a little bit of trig. And if I redraw this diagram, we have the actual velocity, which is always the hypotenuse of the triangle. It's the actual velocity. And if it's traveling 8 meters per second at a 30-degree angle, well, we know that part of that motion is forward, and we know that part of that motion is up. So we just take a look, and we set up our x and our y components, the vertical and horizontal components of this 8 meters per second, and then we just use our SOHCAHTOA rules. So here you can see I've used the sine is equal to opposite over hypotenuse, and I plug in the values I know. In this case, I know the angle's 30, and I know that the hypotenuse is 8, and I just have to solve for the opposite side. So if I multiply both sides by 8, I find 8 times the sine of 30 equals my initial y velocity, which I calculate to be 4 meters per second in the upwards direction. One thing to note is your calculator must always be in degree mode since we're entering degrees and not radians. So always double check that your calculator is in degree mode. If I use the same triangle, but I want to find the x component, well, that's my adjacent side. It's no longer my opposite side, so I'll use cosine. I know that cosine of that 30-degree angle is going to be the adjacent over the hypotenuse. So again, I'll plug in my known angle, my known hypotenuse, multiply both sides by 8 as I factor this out, and I'll find that the initial x component of that velocity is about 6.93 meters per second to the right. So all I've done so far is take my starting velocity, my combined velocity, so to say, and I've just used right triangle geometry to figure out how fast is it moving to the right and how fast is it moving away from the ground. So again, just to kind of conceptually show you this, this is the projectile at the beginning stages. This is the actual path. In both of these diagrams, that projectile is traveling at 8 meters per second along this dotted line. But the initial y velocity only tells us how fast it's moving away from the ground. It doesn't care about how fast it's moving forward. It only tells us how fast it's moving away from the ground. At that same exact time, the x initial velocity doesn't care about how fast it's traveling up. It's telling us at that initial stage how fast forward is it traveling. So this tells us that independently in the vertical direction, the projectile is traveling up 4 meters per second. In the horizontal direction, it's traveling forward at 6.93 meters per second. So hopefully you can see here that it's the identical process to what we've done previously, except you're given the angle, so you usually won't have to find that, and you just use your angle and your hypotenuse to figure out what those vertical and horizontal components are. Now, some of the concepts that will help us with these specific problems, and again, please note in your notes that these only apply for the same starting and ending elevations. These will not hold true for different starting and ending elevations. So please, somewhere in your notes, put that these key concepts are for the same starting and ending elevation. They'll become very important. And I'll explain them as we speak. The first one being that projectiles launched with the same starting and ending elevations will reach their peak at the halfway point. And it kind of makes sense when you think about it. Once this is launched, gravity starts to slow it down, at least in the vertical direction. So as it loses its speed, it takes about half the time to reach its peak. And then the other half of the time, gravity is still pulling it, so now it begins to travel in the other direction. So to put that in more maybe mathematical terms, the time it takes for the object to reach its peak height will always be 1/2 of the total time. So if you know that this takes 10 seconds to travel through the air and then drop to the ground again, you can bet that 5 seconds will be the peak. It will always be half the total time to reach the peak, assuming the object starts and ends at the same elevation. So that's the first important concept. The second one, again, goes hand in hand with what we just spoke about. If this leaves with an initial velocity of, let's say, 10 meters per second, by the time it reaches the top halfway through, it will be traveling 0 meters per second in the vertical direction. So if this had an initial y velocity of 10 meters per second and lost it all halfway through, safe to say that as it starts to travel down, well, it's falling from the same height that it reached. Gravity is still the only thing affecting it. So if you look at all the variables, nothing's different. So whatever I lost traveling to the peak, I'm going to gain as I fall back down to Earth. The difference will be the direction. This object was originally leaving the ground, and at the end it's traveling back down. So what that's basically saying is that if they have the same starting and ending elevations, that y initial velocity will be equal and opposite to the final y velocity. If this is launched up at 10 meters per second, after it goes through its arc, it will crash into the same elevation down in the x direction further at -10. If it leaves at +5 meters per second, it will lose that and then gain it back in the opposite direction and be traveling at -5 over here. If it leaves at 2 in the vertical direction, it will be traveling down -2 at the end of its motion in the vertical direction. So these are the two concepts to realize for same starting and ending elevation. Time to the peak is half the total time, and whatever initial vertical y velocity it leaves with will be equal and opposite to its final y velocity, because all the variables are the same. It's going the same height in the opposite direction. Gravity is the only thing pulling it down. The amount of time to reach the peak is the same from the peak to the ground. Everything is the same, so you'll just get a change in direction. So those are those two important concepts. And I'd like to go through one example so you have a solved out example in your notes, and I'll try and break it down step by step. So we take a look at this projectile. It's launched at a 42-degree angle with a velocity of 20 meters per second. And that's that combined velocity. That is not the x or the y. 3 common questions you might be asked to solve. What total time will the projectile be in the air? How long will it take to rise and fall back to Earth? How far will it travel forward? So what delta x will it travel? And what maximum height will the projectile reach? Hopefully you realize that that will be halfway through the height. Once you reach that peak, what will that total height be? So if I draw out my table, there's certain things we can realize. We know that the acceleration in the x is 0 because it's a projectile, and likewise the acceleration in the y is -9.81 because gravity is the only thing affecting this. Now I'm asking what total time the projectile will be in the air, so I place 0 here because despite the fact that it travels up and back down, if it's beginning at the same starting and ending elevation, hopefully you realize in the y direction it hasn't actually gone anywhere. Its displacement will be 0. It will certainly have a displacement in the x. It will wind up further to the right. But for the y, it goes up and travels right back down. So it starts and ends at the same elevation, so delta y will be 0. Over here, I'm going to do the same calculation I did before. Set up my hypotenuse as 20 meters per second. I have a 42-degree angle. I have some initial x and some initial y velocity, so I've just found these using sine and cosine respectively. So once I know what those are, I can actually come to this same chart and I'll just plug in my known initial values. I know the initial and final for x, which I found here, will be the same because there's no acceleration. And because it has the same starting and ending elevation, I'll also know that the initial y velocity that I found here will be equal and opposite to the final velocity. The only thing that will have changed is the direction. So now I have 3 on one side, 4 on the other actually. And I'll go back to that first question. What total time will the projectile be in the air? So if I want to find delta t, I'm going to use my y variables because I have more of them. And I find if I just use one of my kinematic equations and plug everything in, I can find that that object will be in the air for 2.73 seconds. Now my only word of warning is that you pay very careful attention to your positives and negatives. If you forgot this negative and you left it as positive, when you went to subtract this number, you'd get 0, divide by 9.81 and get 0, and everything would be a big mess. So it becomes much more important to pay attention to the direction and your positive or negative sign in these problems. So 2.73 seconds, just using a kinematic equation and the variables we know. So the only additional step so far has been to find my initial x and y velocity. The second part of the question, how far will the projectile travel forward? Well, again, I'll find delta x. This time I'll use my delta x variables. Now 2.73 could go here and here. I have not written them in to avoid confusion, but 2.73 right now could go here and here. So finding delta x, well, I can use this equation, and I know that the x acceleration is 0, so that whole second term will cancel. So what I'm left with is delta x equals my initial velocity, which is 14.86, times my time, which we found was 2.73, and you can find fairly easily that that object will have traveled 40.57 meters. So far, not drastically different. You just have to use right triangle geometry to find your starting conditions. Now the last question, what maximum height will the projectile reach? That can be a little bit trickier. You have to go back and realize your very important concept that we're talking about the peak. The peak height will be half of the total time. So that being said, if I rewrite my table, but this time just to the variables from the start to the peak instead of the whole motion, I know that the time to the peak will be half the total time. So I'll divide my 2.73, which we found up here, divide it in half, and I know at 1.37 seconds, that projectile will be at its peak height. So I've relisted my variables here. My initial and final are the same in the x because that doesn't change. I have no acceleration, and 1.37 is the time to the peak. My initial y velocity is still 13.38. My final has changed. I'm not saying equal and opposite because it has not ended at the same elevation. We are looking at the time to the peak. At the very top of its motion, that y velocity will be 0 at the instant it reaches the peak. It's about to change direction and fall back to Earth. So all I've done now is say the velocity is not equal and opposite because we're not looking at the whole motion. We're looking at the time to the peak. So I know that the velocity in the y direction at the peak will be 0, acceleration will still be that of Earth, and time is 1.37 seconds. So please try and understand why this is 0 and why my time is cut in half. I'm just adjusting my variables to go from start to peak instead of start to end. Once you've realized that, it's just a matter of finding the right kinematic equation. I've used this one, so I know that my change in y will be my initial velocity times the time, but the time to the peak, plus 1/2 the acceleration due to gravity, times the time to the peak squared. If I plug all that in, I will find that that object reaches a maximum height of 9.12 meters. So just to recap really quickly, these problems are no different initially than our original problems, except for the fact that we have to use right triangle geometry and trig to find some initial velocities. And be careful when you're trying to find the maximum height, you have to analyze from the beginning of the motion to the peak instead of from the beginning of the motion to the end as we did over here. If you can keep track of those and you remember our really important concepts, these shouldn't be drastically different. But just always pay attention that the time to the peak is half the time. And if you're not going to the peak, you're going from start to end on the same elevation, your initial and final y will always be equal and opposite.